Welcome to this, the 22nd class in the physics of materials course. In the last class we examined the idea that when an electron goes through a solid, it is not really reasonable to accept or believe that it has no interaction with what is present within the solid, or that the interaction is featureless, that in other words the potential across the entire solid is exactly flat and uniform. What we realized is that the ionic cores represent locations where the energy of the electron goes down very significantly because the opposite charges are attracting, and therefore there is a certain feature, certain shape to the potential versus position curve that is reasonable to expect within a solid. So what we drew last class, we found that if you had the ionic cores, if those are the positions of the ionic cores, then we found that the potential versus position is more in a detailed manner, looks something like this. So the potential versus position curve looks something like this in a more so this is position and this is potential. Okay, so the curve looks more like this, and it is much more reasonable to actually believe that the electron experiences something like this as it goes through the solid. We also finished off our class by saying that this is perhaps a little too detailed for us to utilize, and to some degree it may not be necessary to capture this picture in exactly this level of detail to utilize it in our understanding of the experience that the electron has. Okay, so we made an approximation to this picture, and so we finished off last class with that approximation. The approximation looked like this: the same positions are still utilized, okay, and some 0 level is set for the energy, and we said that when you come from infinity you see 0 potential, then there is a potential drop, and so the electron actually can be approximated to be experiencing this kind of a potential versus position in distribution inside the material. So wherein the basic idea that once you get close to the material there is a drop in potential is captured by this potential drop here. Then as you get close to an ionic core there is a much more significant drop in potential in a region very close to the ionic core. So those two are the important features of this diagram. Okay, and so those two features have been captured in this approximation, and but otherwise it has been simplified in the sense that these have been made into square steps, so that we have some idea of what is that width, or at least we can do something about we can try to work with the kind of information that this diagram provides. Okay, so this is what we have done as an approximation to what is actually present in a solid, and it is a reasonable approximation. The other aspects of this diagram, this is of course a one dimensional case that I have taken. You could in principle draw a diagram which captures basically the same information that I have shown here in 2 dimensions or 3 dimensions. The diagrams may look complicated, but the basic information they are providing you is essentially what you are seeing in this diagram. So since the information is here and most of the interaction kind of circumstances are also captured in this diagram, it is sufficient that we confine ourselves to this diagram and do our calculations with respect to this, and the results that we will get will in principle be valid for the solid in its more complicated 3-dimensional sense, alright. So therefore this is an adequate enough picture for us and we will work with this picture. Now additional features that this diagram is capturing is the fact that when we use these terms saying a free electron, and I mentioned last class as we finished off that a free electron is one strictly as something that you call a free electron. A strict definition for it is that it is an electron that has escaped the solid, okay. In other words, it is an electron that no longer has any interaction with the solid, it has just gone from the solid, and the nearest that you can think of in an experimental sense is say a photoelectron. So you have some light falling on it, so you see photoelectric effect and electron leaves the solid. So at that point it has been ejected from the solid, okay. So it no longer is part of the solid. At that point position wise it is actually past this location, okay. So it is past this point, so it is no longer interacting with any of the features in the solid, it is out of the solid, okay. So that is a truly free electron, it has left the solid. That would be true also here, anything past that position is also out of the solid, it is no longer in the solid, fine. So then we are also talking of so that is really a truly free electron. So therefore in our previous discussions that we have had when we have spoken of a free electron gas, and I also kept using this term so called free electron gas. The reason I kept saying so called so many times is simply because originally that was thought of as the electrons which were running inside the solid were thought of as free electrons, okay. So originally the picture was that ionic cores were there, each ionic core had released one electron or whatever is the natural valency of that metal, and those collective bunch of electrons were running around through the solid and they were being tabbed or called as these free electrons. But we just now recognize that only when an electron truly leaves the solid does it become a truly free electron, okay. So therefore calling electrons which are present within a solid as free electrons is a bit misleading. They are not really free, they are not free to go wherever they wish, they are free to go wherever they wish within the confines of that solid, okay. So there is a limit within which they have to stay and therefore they are not truly free. So and so they have not really left the solid. So therefore we recognize now that there are those electrons have to be treated somewhat differently, they are not, or at least they cannot be termed the same way. So those are electrons that are actually stuck within this potential well, this slightly shallow potential well which extends throughout the solid represents the potential well corresponding to the idea that electrons are within a solid, okay. So it represents the boundaries of the solid, this potential well represents the boundaries of the solid, or it represents the distance around those ionic cores, around that collection of ionic cores that now represents the extent of the solid. If you are past that point, you say that those ionic cores no longer are interacting with that electron. So if you are past the point, you are out of the solid. If you are within that range, then you are at least the electrons are at least partially being impacted by those ionic cores that are present there, okay. So to the extent that they are even partially being impacted by those ionic cores present there, they are now within the solid, within the extent of the solid. So electrons that we have previously been talking of, which are those electrons released by the ionic cores but are running within the confines of the solid, are actually staying within this potential well, okay. So in this diagram we have to recognize that that is what this potential, the first shallow step that you see here is exactly that. It is that idea and that concept that the electrons which are now within this region, within this starting from here up to here, okay, they are electrons which are but are within this potential within this shallow potential well, okay. So this is the term well is used simply because it is a deep it is going deep inside the material. So in terms of depth, I mean it is not deep within the material, in potential sense it is a depth, so therefore this term well is being used in keeping with some physical picture. But the basic idea being if the electrons are within this shallow potential regime and therefore stuck within this solid, they are now referred to as nearly free electrons. They are not truly free electrons, they are simply nearly free electrons, okay. So electrons that are here are nearly free electrons. So nearly free electrons are confined to stay within the solid due to the presence of this small potential well, okay. So that is what a nearly free electron is. Then we have electrons, all the remaining electrons in the solid. Okay, I mentioned we have always discussed this so far, that we have only the ionic cores or the atoms to begin with have released one electron each, and therefore now there is an electron running around through the solid, plus the remaining electrons stay along with that ionic core or the atomic core, the core of the atom, which now is now ionic because it is positively charged. So we call it an ionic core. So all the remaining electrons are now still stuck with that original location of that atom. So in other words, when I mark these out as the locations of those crystal lattice, so to speak, and therefore there is an atom at each of those locations, assuming that that is the crystal structure that we are discussing, then all the electrons remaining, whatever the electrons, if there are 50 electrons, then 49 of those electrons are stuck to this stuck to that that general location. Only one electron is left to run free across the solid for every ionic core that is present. So those 49 electrons, all the remaining electrons of that atom are actually stuck to this much deeper potential well, okay, and therefore they are also stuck to this narrow region in space. So these are called bound electrons. Okay. So bound electrons stay within a very small confined small region along on either side of that location of that ionic core, and they are sort of stuck to that ionic core. They are not free to run even the extent of the solid. Okay, so this so an ionic core is 1 angstrom across, let us say, or even less, say 0.8 angstroms across or whatever, some such small dimension. So 49 electrons, if we assume an arbitrary number like 50 electrons in that per atom, 49 electrons are stuck to within that 1 angstrom of that location. That one remaining electron is stuck to the remaining is left to run across the solid. Okay, so that is the difference, fine. So that is the, in terms of dimensional scale, that is the difference. So a bound electron stays within that region that we would normally call as an ion or an ionic core or an atom, and so that is, they are stuck to this deep potential well. The nearly free electrons are stuck to the extent of the solid. They are free to run across the entire solid, they are stuck to the extent of the solid, and the truly free electrons have left the solid, fine. So these are the three definitions that we are using, fine. So that is the first thing we need to recognize. The second thing I will also point out is something that I just mentioned, but I will elaborate on it. This size scale here is of the order of 1 angstrom. So if the potential well we are talking of is of that angstrom scale, okay. So that is a very small dimension, 10 power minus 10 meter. The length of the solid, the extent of the solid is something that is huge, relatively speaking. You can have a block of metal that is 1 meter long, okay. So 1 meter would be a distance that is this large roughly, okay. So that is a pretty large distance, fine. So when we talk of a nearly free electron, it is free to run this distance of the order of 1 meter, okay. In a straight line, it is of the order of a 1 meter distance. It may take any other convoluted path, but its straight line distance displacement that it could have is 1 meter. That is the distance that it can travel. So that is 1 meter. So we can talk of this distance being 1 meter or half a meter or a millimeter or a centimeter. It is in that size scale, 10 power minus 1 to 10 power minus 2 meters is the kind of size scale, depending on the object that you are talking of, if it is a wire or any such thing. So that is the thing. You could have very long wires also, so we could have several meters long, whereas this bound electron is confined to a size scale of the order of 10 power minus 10 meters, okay. So it is an angstrom. So there is a massive difference in orders of magnitude in the confinement level. We call this idea confinement, that is that the electron or whatever is the species that we are talking of, in this case an electron, has to stay within a certain region, okay. So it has to stay within a certain region because of the conditions that it is experiencing. This idea that an electron has to stay within a certain region is called confinement, okay. So that basic, it is just a straightforward description. It is a confinement. The electron is confined to stay within that region. A bound electron is confined to stay within about an angstrom of that location. A nearly free electron is confined to stay within a meter of that material, just to give an order of magnitude example. A free electron, a truly free electron, is really free. It can, there is no bounds on it. It is not confined. It is free to run across the entire universe, so to speak, okay. So that is the way we look at the description. So that is the other information we have. Now the third thing that I also want to highlight here, when while we still have this picture, before we proceed forward, is that in all this time we have done calculations. First we started out with the Drude model and we called those electrons as so called free electrons, did some calculations that did not work out completely acceptable to us. So we changed the statistical distribution from Maxwell-Boltzmann statistics to Fermi-Dirac statistics and redid the calculations. We came up with some terms such as Fermi energy and we came up with a new distribution. Now this is also an energy versus position curve. Okay, so we have energy here in this y axis, we have position on the x axis, which is what we have put down here. Okay, so potential energy I have put here, but basically it is energy versus position is what we have here. So in this diagram, the first thing I want you to understand is that I would like to highlight what it is that we have been doing the calculations for. Okay, so our calculations were not for those this arbitrary example I have taken of 50 electrons being atomic number being 50. Our calculation was not with respect to these 49 electrons that are stuck in this deep potential well. We were not bothered about these 49 electrons which were the bound electrons. So our calculation did not really look into this picture, we did not really bother about. Why we did not bother about it? Because in principle for the properties that we are interested in, those are not the electrons which appear to be contributing in any significant way to those properties. So that is the reason why we did not look at it at that point in time. There are other phenomena for which these electrons also make a difference. Okay, so therefore you would have to look at that, which we have not done so far. So that was not of relevance to us. So we did not really bother about these 49 electrons that were here per atom. All our calculations were with respect to that one electron per ionic core, which contributed to this so called electron cloud, which was running across the extent of the solid. Okay, so therefore all our calculations were only with respect to these nearly free electrons. All the calculations we did so far and whatever analysis we tried to do, whatever results we tried to get, whatever predictions we tried to make, were only with respect to the behavior of these nearly free electrons. Okay, so that is the thing that we need to I would like to emphasize here. We did not really bother about these bound electrons, but they are there. It is not that they are not there, they are definitely there within that solid, but we did not really bother about them. That was not because they did not really seem to impact the property we were interested in. We focused our attention on these nearly free electrons, we called them so called free electrons, etc., and then but we did our analysis only with respect to these nearly free electrons. So whatever parameters we came up with and whatever analysis we did was with respect to this. Alright. So what did we come up with? We came up with something called Fermi energy. Okay, so we said that you take the energy levels from the lowest energy level upwards and you start filling them up. You will reach a certain high energy level, at which point in time you will run out of those nearly free electrons. Let us keep calling them nearly free electrons now, because that is what they are at this point. So we will run out of those nearly free electrons. That highest energy level is then called the Fermi energy level. Okay, so now with respect to this picture, so this is energy, and that is the direction in which it is increasing. Okay, the way this picture is drawn is based on the convention that when an electron is very far from a solid, its potential energy is 0 with respect to that solid. Okay, so when it has no interaction, it is 0, and because it is also oppositely charged with respect to those ionic cores that are present there. Okay, so therefore its potential energy is 0. As you bring it closer and closer and closer to that solid, its potential energy becomes more and more negative. It is, or in other words, it is decreasing in energy. Alright. So in terms of our convention here, this potential energy would then correspond to 0, because you are going further and further away from the solid. These are all negative potential energies. Okay, so this is 0 in this energy scale. Fine, and this is decreasing energy. Alternately, this is increasing energy, but it is increasing from a negative value all the way up to 0. Okay, so in this picture, when we say that we are talking of the energy levels of the nearly free electrons, and we are starting from the lowest energy level possible and filling them up, what we are basically saying is, in this range of energy, first of all we recognize that this is the range of energy that we are talking about, and in this range of energy we are saying that from the lowest energy possible we are filling the electrons up. So we are definitely going up in energy level. Okay, so we are adding as we fill the electrons up in the various available energy levels, we are definitely going up in energy level. However, with respect to with respect to this what shall I say, coordinate system, that coordinate axis that we have used here, and with respect to this concept that far away from the solid the potential energy is 0, these are all still negative energy levels, okay, negative in energy. So that is something that I just want to highlight, so that you are at least aware of how the because when we do the calculation it may not appear that way, but when we try to put the information together in a single picture, we have to be sure of where each one comes with respect to the other, okay. So we have to know the relative positions of all these energies, therefore we need to pay attention to this detail, that in the normal convention of how these things are done, the energy of an electron far away from the ions is set at 0, and therefore all the other energies that we are drawing on this picture are negative. That is number 1. Number 2, the nearly free electrons are stuck to energy values which are in this range with respect to this picture. This range is also still consisting of negative values only with respect to this convention that far away is 0, but within these negative values you start at a much lower energy level here and you start filling it up, filling up all the energy levels, and then at some energy level you run out of electrons, okay. So we will assume that this is the energy level at which we run out of electrons, run out of the nearly free electrons. This has been attained by first taking all the states that are available to us, filling them up one by one, and then we finally run out of all the nearly free electrons when you reach this energy level, alright. So therefore this energy value is now what we described in our previous calculation as the Fermi energy level, so which we listed as E subscript F. So this position here is E subscript F. So this is the Fermi energy, okay. So the calculations that we did previously refer to this set of electrons which are the nearly free electrons. In that calculation we came up with something called Fermi energy. That Fermi energy in this picture would show up something like this, okay. So that is how the information that we have the concepts that we have discussed in some of our earlier classes relate to the concept that we have discussed in the last class and we are discussing now, okay. So that is how they relate. So this is the Fermi energy. In this also, having come this far, it is of interest to put in one more piece of information before we proceed, which is simply that when we talk of, say, the photoelectric effect, we talk of something called the work function, okay. That is the amount of energy that is required to pull an electron off of that solid, that is the work function. Now in this picture the work function is now the amount of energy required to pull the highest energy level, the electron containing the highest energy. So in other words, in the solid, whichever is the highest energy electron, what is the energy required for you to pull it out of the solid? The highest energy level electron is sitting at the Fermi energy, right, and to get it out of the solid, to make it escape from the solid, you have to get it up to 0. In this scheme of things, this is 0 energy, the topmost level is 0 energy. So you have to get it to 0. At that point in time you can legitimately say that the electron has escaped the solid. So therefore this difference here, that difference is the work function. So okay, so this here is the work function which is typically designated or denoted by phi, okay. So this is the Fermi energy, and the difference in energy between the Fermi energy and this 0 that we are setting for the scale then is the work function, okay. So this is how several of the concepts that we have discussed with respect to quantum mechanics, with respect to Fermi Dirac statistics, and with respect to what a solid is, how the electrons within the solid are, how the ionic cores are, what is the impact of all of these on this picture and so on. This is how all of them come together, and this is how they relate to each other, okay. So therefore this is a picture that is useful to have in mind, and it is useful to understand what is the significance of all of this information, alright. Okay, so now temporarily we will conclude this particular discussion. We will now proceed to another discussion wherein we will start using these features, okay. So we understand how this picture came about, we will use this picture now to see what is it that we can predict about the material, okay. So we will start using this picture. So to do that we will actually we will do it in 2 steps. First we will look at electrons that are truly free, in other words electrons that have escaped the solid, okay. So that is what we now mean by saying truly free electrons, they are free electrons, they have escaped the solid. Then we will look at electrons which are trapped in a potential well, okay. So such as the electrons which are trapped in this shallow potential well here, or the electrons that are trapped in this deep potential well here. Okay, so both of these we will look at. So we have to look at in fact 3 cases effectively, but actually strictly only 2 cases, either it is out of the material where it is completely free, or it is in a potential well. Okay, and we will make some classification on how deep the potential well etc. is in a bit, but that will assist us in our calculations. But these are the 2 that we will look at: free electrons and bound electrons, regardless of whether they are totally bound or they are just nearly free or whatever, they are deep bound in some potential well. So that is what we will differentiate between. Now to look at the behavior of those electrons, these free electrons and bound electrons, or free electrons and nearly free electron, to look at their behavior, to differentiate between their behavior, we have to actually utilize all the quantum mechanical principles, alright. So which we will do, but before we do that, we will first do it, we will look at this this concept and this picture from a much more simpler approach, a much simpler approach, which will still give us essentially the same result. So what we will do is we will first look at this in a much simpler approach, and then we will use all the quantum mechanical, a much more rigorous quantum mechanical approach. Both of them will give us the same result, therefore it is acceptable to us, but by starting with the simpler approach you will get a better feel for what it is that we have done, alright. So that is what we will do. Now the what we are trying to do, okay, at the end of it we are trying to look at the behavior of the electrons. We would like to see what they can do, what they can't do, and understand and that is with respect to the conditions that they are facing, maybe the potential well they are facing etc. So with respect to the conditions we want to know what can the electron do, what the electron can't do, that is the basic question that we are trying to answer. So to do that we would like to see what is the behavior of the electron, so we will look at it. So quantum mechanical description says that we have a wave particle duality, which is something that we already looked at, we discussed. So we can look at electrons as particles, we can also look at electrons as waves. So for the moment we will look at it as waves and then see what it is that we can obtain from this picture. Okay. Also we wrote the de Broglie wavelength as of a particle having a momentum p as p lambda equals h. Okay, so this is the de Broglie equation. We can rearrange this marginally. We will have implies p equals h by lambda, and for convention's sake in fact we tend to use h by 2 pi, so we can write this as h by 2 pi and also this as 2 pi by lambda. Okay, for convention's sake this is done, we will see that that convention later, but basically conventionally this is the way this is done. This h by 2 pi is also designated as h bar. So if you see books you will suddenly see sometimes you will see h bar being used, sometimes you will see h being used. This is how they relate. H by 2 pi is the same, is what is called h bar. Okay, so h bar is what this is, and this quantity here lambda 2 pi by lambda, okay, it has the dimensions of 1 by length, because lambda is in the denominator, lambda is wavelength, so lambda is in the denominator. So here p is momentum, h is Planck's constant, lambda is wavelength, and lambda is in the denominator. So this quantity here has the dimensions of 1 by wavelength and is actually referred to as a wave vector. Okay, so this is referred to as wave vector and is designated as k. Okay, so this is how they relate. When you talk of k, you are actually, it is the inverse of the wavelength, and it is a wave vector in the sense it is talking of it is just not just the length of the wavelength, it is also the direction of the wave. Okay, so therefore that is an important quantity. So when you write h bar k, it is the same as writing h by lambda. Okay, so because we are simply divided by 2 pi multiplied by 2 pi, so we have made no difference to this equation. This is divided by 2 pi, this is being designated as h bar, that is being designated as k. So h by lambda is nothing but h bar k. Okay, so that is the thing that you need to understand. In much of our analysis we will tend to keep using h bar and k, so this is, it is important to at least be alert to the fact that these are fairly straightforwardly associated with the quantities we are already accustomed to. Okay, so p is this, and we also say that, you know, we also write p is mass times velocity, energy is half mv square, right. So these are the conventional definitions for momentum. P, linear momentum, P is mass times its velocity, and energy is half mv square. So if you therefore if you try to relate energy and momentum, it is simply energy is m square v square by 2m, right. If you do this, you will get the half. You can multiply, essentially all I have done is I have multiplied the numerator and denominator by m. So m square v square by 2m is what this equation is, and the numerator is now p square because p is mv, okay. So therefore E equals p square by 2m, okay. So this is just a general relationship between energy and momentum, and if you see P as h bar k, this is h bar square k square by 2m. Okay, so this is just a relationship between energy and momentum, or energy and wave vector, momentum and wave vector. All these relationships are there. As necessary, we will utilize them. Okay, so right now we need not. We just need to be aware that this is the way we need to look at it. Okay. Our immediate actually our immediate concern or our immediate task is in fact to understand for electrons that are present within a solid, under the various circumstances that they are present within a solid, or under the various circumstances that they can exist, what restrictions are there on the wavelengths that they can adopt. Okay, so that is the piece of information that we wish to find out. What are the restrictions on the wavelengths that they can adopt? At this time it may seem like a a somewhat detailed piece of information that we are looking for, but later as we utilize that information we will see why it is of use to us. Okay, so that we will see little later, because it basically says what is the energy levels that are allowed for the electron. We have always said that energy values, that we said that there are energy levels E0, E1, E2, E3, E4 and so on, and that is how we filled those electrons, right. We took the electrons, the nearly free electrons, and filled them across those energy levels. Now the point is, we did that sort of in an arbitrary way. We assumed that E0, E1, E2, E3 etc. existed within the solid. We have not really looked at how they may exist or why they exist, right. We have just assumed that they exist. So why should they be E0, E1, E2, E3? Why cannot it be continuous energy values? Okay, so that is an important piece of information that we need to understand. First of all, why is it that energy cannot be continuous, and or at least we are saying that in our system it is not continuous. We just assumed it is not continuous. We would like to see why it should not be continuous. That is number one. And when it is not continuous, what are the values of energy that are those values? So far we have simply said E0, E1. What is E0? What is E1? What is E2? That is not something that we have discussed, but they are very important features of all the calculations we have done. Okay, so our task at the moment is to actually explore that region of our discussion, and then utilize those results as we see fit in the subsequent discussions. So in other words, when I say what is that value of E0, what is the value of E1, etc., I would like to know, and E is related to the wave vector here in this manner. The h bar is a constant because it is a Planck's constant. Mass of the electron is a constant, so that is also a constant. So really when we say E has specific values, E0, E1, E2, E3 etc., when we say that E has specific values, all we are saying is in this relationship the allowed values for the wave vector, therefore the allowed values for the wavelength of the electron are also only specific values, right, because h bar is a constant, 2m is a constant. Therefore if this has only specific allowed values, this parameter can also only have specific allowed values, and this parameter is the wave vector, which is 1 by wavelength. Therefore wavelength has only specific values, allowed specific values. So we want to understand why is this the case. Okay, so why is it that electrons in a solid appear to have only certain allowed wavelengths, and that they are not allowed to have whatever wavelength they wish. So that is the question we wish to answer, and as I said, strictly speaking the way to answer that question is to really look at the quantum mechanical behavior in the quantum mechanical approach, and then see what is the answer. And we will do that, but we will take a much easier approach to answer that question and then take the quantum mechanical approach to answer that question. So let us look at it this way. We are aware of waves on a string, so I will just say that we have a wall here and we have some string. Okay, so this is a string that is now attached to a wall at one location, and it is sort of lying loosely lying there. alright. So now in this situation, so this is wall, this is some string. When you have a string that is tied to a wall at one location and the other location is free to hang around, what are the question that we need to answer is what are the wavelengths that can be supported by this string. Okay, so what are the wavelengths that can be supported by this string in this particular situation where one side of the string is tied, the other side of the string is free to hang as wherever it wishes. Now in this situation, since this end of the string is free, the answer is it can support any wavelength or any and all wavelengths in this case. Why do I say that? Because this end is free, whatever wavelength you say, supposing I say the wavelength is a very large wavelength, this string will take this part of that wavelength. Okay, if it is a very short wavelength, this string will take this, and we will assume these are all sinusoidal waves. Okay, so it can be a small wavelength, a very tiny wavelength, or a very large wavelength. Because this end of the string is free, it can support that wavelength, there is no problem. It will just take whatever part of the wavelength that it can with respect to its length, and it will take that wavelength. If it is even larger wavelength, it will take that, which means the string sort of ends here and it is part of that very large wavelength that is there, alright. So a string that is tied only on one end can support any wavelength that you desire, okay, or it can take a shape that is consistent with any wavelength. There is no restriction on the wavelength that it can support, absolutely none, it is free to do whatever it wishes. You can take an extremely tiny wavelength also, it will do it, very large wavelength also it will do it, because there is no restriction on the string, especially on one end, it is free to do what it wishes. Okay, so that is a very important statement we can make about a string that is in this format. Now we will take another string. Okay, so now let us say that it is now tied between two, it is basically tied at two locations on two walls. So wall here, and this is a string. Alright. Now we ask ourselves exactly the same question, what are the wavelengths that this string can support? Okay, so that is the question that we wish to answer, what are the wavelengths that this can support? What we will find is that because the two ends are tied, okay, in other words, if when we talk of a wave, okay, so when we talk of a wave, we first of all we have some origin about which this wave is being drawn. So it has to start somewhere, if it is a sinusoidal wave it has to reach a maximum, it has to come back to 0, it has to go to a negative maximum, come back to 0, that is the way we look at a sinusoidal wave. So we will say this is amplitude and this is the with respect to time, let us say time or distance, we will say distance. Okay, or position, fine. So it has to go to a maximum, come back to 0, go to a negative maximum, come back to 0. Now when you say that two locations are fixed, okay, so and they have fixed like this, they are fixed at the same height for example, let us say, so they are fixed, which means that no matter what you do, this position has to be at 0 displacement with respect to this axis. Okay, so the displacement of this position is 0, it cannot move from this position, it is stuck here. Similarly the displacement of this position with respect to the horizontal axis is 0, it cannot move from there, so it is stuck there, right. So this wave, this string can only adopt shapes wherein one end still remains at 0 and the other end also still remains at 0. So if you place this constraint, the largest wavelength that it can support is one where half the wave is what this distance represents. In other words, as you can see here, half the wave, at half the wave this is at 0, this is at 0, right. So except that is on the positive direction, this is on the negative direction. So half the wave will correspond to this length, which is this length here, and therefore this string can support in principle a wavelength which will correspond to double this length. Okay, it can be part of a wave, it is part of a wave, it can maintain the shape consistent with a wave where the wavelength is twice what this length is, that is all. That is the largest wavelength it can support. Below this also it can support various wavelengths, however it cannot support all wavelengths below it, because you are always placing the restriction that these two ends have to be at 0. Okay, so at x equal to 0 the value of this wave should be 0, at x equal to whatever this distance is, a, let us say I will call this a, if a is the distance between the two walls, at x equal to 0 this distance displacement has to be 0, at x equal to a this displacement or this value of this wave has to be 0. So those two have always got to be true. So therefore what will happen, you can only, if you look at this those two restrictions, what it means is you can have a wave that looks like this, or you can have a wave that looks, the next smallest wave that you can hold will be one where it will look like this. Okay, so in other words a can either be lambda by 2, in which case this is the lambda, right, a can either be lambda by 2 or it can be lambda, in other words 2 lambda by 2 or 3 lambda by 2, 4 lambda by 2, etc. It can only be n lambda by 2. So therefore n lambda by 2 equals a. Okay, these are the only values of lambda that are allowed. Okay, so I have just done some calculation, let us understand the significance of this calculation. The calculation says that if you tie a string on two ends, you are now faced with a situation where the wave shapes that the string can demonstrate are ones where the two ends are fixed. The only way those two ends can be fixed are when they are at, one is at 0, the other one is either at lambda by 2 or at 2 lambda by 2 or at 3 lambda by 2, etc. It has to be some integral lambda by 2, at lambda by 2 it reaches 0, right. Since it is at since it reaches 0 at lambda by 2, only at subsequent, if you add on half a wavelength, half a wavelength, half a wavelength, etc., only then you will keep coming back to that 0 position at the other end, given that one end is fixed, fine. So but you still have only a total length of a. Okay, so when I am adding up lambda by 2, the total length has to still got to be a. You cannot, so you can in other words the wavelengths can keep getting smaller and smaller and smaller, such that as you go through the entire wave at some lambda by 2 you arrive back at this point. You start with simply lambda by 2 arriving back at this point, this is lambda by 2 plus lambda by 2, so now 2 lambda by 2 you arrive back at this point, or you can do 3 lambda by 2 which will bring you back to this point, 4 lambda by 2 you will come back to this point, and so on. So you can keep on doing this such that the total number of half wavelengths that are present within this region is some integral value, some integer value. Okay, so some 24 lambda by 2, 36 lambda by 2, whatever, so some integer value of lambda by 2 is what this this set of constraints permits on this string. Okay, so we will look at that, we will now put this information down. So we will come back here, we have a free string implies no restrictions on lambda that can be supported. Right, for a free string there are no restrictions on the value of lambda that can be supported, that is what our diagram showed us. Okay, so that there is no restriction of on the value of lambda it can support, any value of lambda that can be taken. String fixed at two ends, in our case a free string also meant or fixed only at one end. okay, a free string or a fixed or something that is fixed only at one end, no restriction on the value of lambda that can be supported. A string that is fixed at both ends, okay, a string that is fixed at both ends, we find that first of all not all values of lambda are supported, okay. So that itself is a very important piece of information, the fact that not all values of lambda can be supported. Right there this situation is different from this situation. In the top here any value of lambda can be supported. First thing we find out is that when you tie down both ends of the string, not all values of lambda can be supported. So that is the very first piece of information that we find. Over and above this information we also realize that we are able to find out the condition for the lambda for it to be supported by the string only. So that is number 1. So number 2, only values of lambda such that n lambda by 2 equals a, which is the distance between which is the distance within which that string is confined, can be supported. Okay. So we see immediately, we understand that there is a difference in the two cases that we have just looked at. Okay. So this is, I put it down here because we are going to relate to this information here, that is the reason why I have put it down along with this information. We realize that not all values of wavelength can be supported, and we realize that it is not just that, more specifically only when n lambda by 2 is equal to a, which is the distance within which that string is confined, only those values of lambda corresponding to this can be supported. So you can write this the other way, therefore lambda equals 2a by n, those are the values of lambda that are permitted. Okay. So that is the restriction that we have now recognized in this situation. Now if you look at our equation here, we have energy and we have wave vector k, which is simply 2 pi by lambda, right. So we already have a relationship, given that there is a wave, okay, given that there is a wave, we have a relationship between the energy of that wave and the wavelength of that wave, we have that relationship. So that is an independent relationship, it simply says that if this is the wavelength, this is the energy, that is all it says. What we are trying to look at is that given our system, we find that we have a certain set of possibilities. We have a possibility where a string is free, or at least it is tied only at one end, which means it can adopt any value of wavelength. So there are no restrictions on the value of wavelength for this string. If you now take that information and employ it on this equation where E equals h bar square k square by 2m, the consequence is that we find that since there is no restriction on the value of lambda, that any value of lambda can be accepted or sustained by that string, there is no value, there is no restriction on the value of k, which is simply 2 pi by lambda, alright. So since there is no restriction on the value of k, which is 2 pi by lambda, therefore there is no restriction on the value of energy, okay, because in other words continuous values of energy can all be demonstrated by that system. Okay. So the for a case of a string that is tied only on one end, all values of lambda are allowed, therefore all values of k, which is equal to 2 pi by lambda, are allowed, therefore all values of energy which are directly which is directly related to k by this equation, E equals h bar square k square by 2m, all values of energy are permitted. There is no restriction on the value of energy that can be demonstrated by a system which is a string which is tied only at one end. Okay. So that is the significance of the discussion that we have had. E equals h bar square k square by 2m. So in our first case of a string that is tied only at one end, all values of k are permitted, therefore all values of energy are permitted. Therefore if you make a plot, or if you list all the values of energy that can be shown by a string tied at only one end, you will find that all the points are continuous. I mean there is no gap, any it's just as continuous set of energy values, there is no you do not have to jump between energy values, it is all continuous, all energy values are permitted by the system. On the other hand, when you look at a string that is tied at both ends, okay, a string that is tied at both ends, we find that immediately we find that not all values of lambda are permitted in that system, because that system cannot consistently show you all those values of lambda subject to these two constraints. Only specific values of wavelength are permitted, which is related to the distance within which that string is confined. So if a is that distance within which that string is confined, the values of lambda that are permitted are such that n lambda by 2 equals a, where n is any integer 1 2 3 4 5 6 all the integers you can use. So only values of lambda that are permitted are 2a by n if you just rearrange this, okay. So therefore those are specific values, those are not continuous values, okay. So when I say 2a by n, you cannot have 2.1 a by n, you cannot have 2.2 a by n, you can only have 2a by n and those n values can be 1 2 3 4, that is all you can have, right. So so therefore you cannot have so you cannot have 2a by n, I mean you cannot have 2a by 1.1 n, that you cannot have, right. So all those things you cannot have, n has to be an integer, so that is the bottom line, n has to be an integer. So only specific values of wavelength are allowed, and so you can make a table, you can make the table of the specific values of wavelength that are allowed. What would be those wavelengths? It will be 2a by n equals 1, so 2a, 2a by 2, 2a by 3, 2a by 4, 2a by 5 and so on, and a is some fixed value, a is some distance, it could be 1 meter, it could be half a meter, it could be 1 centimeter, it could be an angstrom, whatever it is, but it is a fixed value, okay. So it is a fixed value and it has the units of length, okay, so within which that string has been confined. So now that is a fixed value, so the only values of lambda that are allowed are 2 times that length divided by an integer, so 2a by 1, 2a by 2, 2a by 3, such are those values that are now permitted in this system, and those are discrete values, so you can actually write a table of those values. For each of those values you will have a certain energy given by this equation, okay. So for every value of wavelength that is permitted, you can write 2 pi by lambda, therefore there is a specific k that is permitted, k vector, wave vector that is permitted, therefore there is a very specific value of energy that is permitted. The next value of energy that will be permitted will not necessarily be adjacent to this energy level, you have to find out the next value of lambda in your table. So first value is 2a by 1, so therefore it is simply 2a, for that you will have an energy value. The next value that of wavelength that is permitted is 2a by 2, right, so for which you will have another energy value. In between there is no energy that is permitted, you have the first energy level, the next energy level, in between there is no energy level that is permitted. The same thing will happen next, you again go to 2a by 3, you will have a particular value of energy. Once again between what you got for 2a by 2 and 2a by 3, in between no energy values are permitted. So the important idea that we have to take from this class, the very important idea that we have to take from this class is that in our analogy of a string that has been tied to two locations, in other words a string that is confined, the confinement of the string causes a situation that all energy values cannot now be demonstrated by that system, only discrete energy values can be demonstrated by that system. In other words, the most important idea that we have to take from this class is that confinement leads to quantization, okay. So we will write that down, we will write it here. The idea that only specific energy values are permitted is what this quantization is all about, that you have a certain energy value, if you leave it, the next energy value is some distinct step away from it, it is not immediately next to it, it is some distinct step away based on the allowed next allowed wavelength, okay. So that idea is quantization, you have one value, then another value, then another value and so on, those are discrete values and this is quantization. That has come about only because you have confined the string to stay between those two locations, it is tied between those two locations, because it is confined this has occurred. When it is not confined you have continuous values, you do not have quantization, okay. So that is the difference between a free string and a string that is tied in two locations. So confinement leads to quantization, okay. So this is the most important idea that we have for this class, which we have discussed. We will halt here. In the next class we will actually look, as I said, we have done this with a simplified analogy of a string. We will actually do it in the in a more puristic quantum mechanical way. We will look at the quantum mechanical approach of handling exactly the same problem and see whether that result that comes out of it actually is similar to, we will find that it is in fact identical to this result that we have obtained here, and therefore this picture that we have used is actually useful for us because it is giving us a result that is reasonable with respect to what we are looking at. Okay, so we will halt here. We will look at, we have concluded that confinement leads to quantization. We will explore this idea a little bit more in the next class and then take it forward from there. Okay, thank you.